Thank you very much, and thank you all for being here today for my HDR defense, which is titled Advancements in Aerial Physical Interaction. And today I will present my work that I did in this field that goes from the design and control of aerial manipulators till the collaboration among multiple aerial manipulators, including also interaction with humans. So aerial physical interaction is a field that is studying how to make aerial robots not only be able to fly with avoiding obstacles, for example, to inspect environments with camera, but actually exploit those contacts to perform physical work, manipulate objects, and do physical work. So this field started about, let's say, 10 years ago, with the ambition of opening the door to new applications that requires physical work in high altitude, like, for example, construction, inspection and maintenance, and others. But despite the works that a lot of researchers has been already done, the very promising results that we obtain, and also the appearing of some first commercial solutions, we are still far from having aerial manipulators able to perform complex manipulation tasks in real environments. But why there is still this gap between what an aerial manipulator can do and instead what a ground manipulator can do, which, I mean, is able to perform a complex manipulation tasks since many years? Well, the very first source of challenges is the type of base. In fact, a ground manipulator is fixed to the ground, while an aerial manipulator, the arm is attached to a floating base system, which is very more difficult to control. Let's make an example. So as soon as the arm moves, because of some dynamic reaction, so there are some torques and force that are applied to the base of the system. But in a grounded manipulator, those forces and torques are passively directly compensated by the reaction forces of the ground. While on an aerial manipulator, those reaction forces, they need to be actively compensated by the floating base. And this is very similar when the robot gets into the interaction with the environment, so there are interaction forces applied to the end effector. The second source of complexity is also the type of actuation. While on grounded manipulators, normally those systems are controlled by very accurate torque control motors. On the other side, on an aerial manipulator, we see inaccurate, normally servo motors to control the arm, to make the arm lightweight. But not only this, also the platform itself is then, the aerial platform itself is instead actuated by propellers that generate forces pushing the airs. But due to turbulences and very complex aerodynamic effects that are difficult to model, then the precise control of the force produced by propeller is very challenging. Therefore, to address all this problem, I believe that it is required a very deep and formal analysis of the dynamic properties and capabilities of those systems to then be able to design new dynamic controller and motion planners that can really perform good for physical interaction. So my journey in the realm of aerial physical interaction started quite some time ago during my internship at the Max Planck Institute, where I first started working in robotics. There, fascinated by this domain, I then decided to start a PhD at LAS under the supervision of Dr. Franchi and Dr. Cortez. And at the end of this one, I decided to stay in LAS for another year and a half, more or less, to finalize some works, start new works through collaborations, and also some independent work. And also to improve my management skills, I decided to stay to be the technical leader of the last team for the robotic challenge Ambizirk. At the end of this one, I then moved to ETH Zurich in the ASL group, where I was the leader of the micro aerial vehicle team. And finally, in November 2022, I then got a permanent position here at INRIA as an INRIA researcher within the Rainbow team. So to start my journey, so at the beginning of my PhD, aerial physical interaction was not that advanced, or actually the question was still if aerial physical interaction was even possible. That's why during my PhD, I started analyzing system with the always increasing complexity, starting with the simple aerial manipulators with a passive link, like cables or bar, to then move to active links, so where there is an active manipulators, endowed on either under-actuated or fully actuated aerial vehicles. So those preliminary results, let's say, were able to show how an aerial robot can actually interact physically with the environment. And thanks to those results, and of course, all the work of other colleagues, I will say that after my PhD, the community managed to show the feasibility of aerial physical interaction, but mostly on indoor environment using motion capture systems in very structured environment where the modeling is known, and also for very simple tasks like pick and place, or at best what we call push and slide on static surfaces. But even in those very simplified conditions, as soon as there are additional sensor noise, disturbances, or uncertainties in the environment, performances and robustness can decrease drastically, often leading to the failure of the system, as we saw many times during the robotic challenge Ambit-Zirk. Therefore, I believe we are still quite far from having real aerial manipulators that can perform complex tasks in a real environment. This is why at the end of my PhD, I basically took this as a main driving motivation and goal, which is, again, designing aerial manipulators that can perform complex tasks, for example, for precise agriculture, construction, inspection and maintenance, in real environments like oil and gas, or power distribution plants. But to reach this goal, there are still many gaps and challenges to be addressed. So, for example, considering single robot operation, aerial manipulator needs to be very robust against uncertainties and disturbances, and being able to not only interact with the static environment, but also with dynamic and articulated objects. And although this is a must, for some application might not be enough. In fact, because of the complexity of some tasks, robots might need to collaborate with each other. So the task might require multiple robots to perform the task, or even the interaction with human. Therefore, my goal was to design aerial manipulators with enhanced aerial physical interaction capability to perform a complex interaction task in uncertain and dynamic environment. And to reach this goal, I started my investigation along three major axes of research. The first is precision, robustness, and safety of single robot operation. The second instead is the collaboration among multiple aerial manipulators. And finally, the third is the collaboration even with humans. And to perform this research, I mainly based on what we call holistic method, meaning that I try to address all the main axes of robotics, not as independent modules, but rather as very interconnected aspects of a single system. And relying on my background, I mainly focus on the conception, modeling, and control of those systems, trying to provide a formal proof of stability and guarantees, but without still completely neglecting, anyway, the links with the perception and motion planning. So the investigation of three axes of research has been done in different way along my career. In the specific, the investigation about single robot operation has been done mainly at ETH Zurich, where I was leading the MAV team along this for this objective. On the other hand, the multi-robot aerial physical interaction has been an investigation that started at LAS, also with Antonio, and then continue with the collaboration with him and also other researchers and students at LAS and also University of Padua. While the third research axis that is about having aerial manipulator interacting with human, this was an investigation that I autonomously started, being really curious about the topic, and so I independently started it at LAS, and then I instantiate it at ETH, where I also managed to get my own funding to continue this very interesting topic. So because of the so today I will try to provide a broad overview of all the work that we have been doing along each axis, but because of the limited time, I will mainly go in the detail only of the first axis. So let's jump into this one that is about the improving performance of single robot aerial physical interaction. So the first goal was to improve precision, because even when we were using a fully actuated aerial vehicle, for example, the one of ASL that is even omnidirectional, which means that it can exert forces in multiple directions while being able to also control position and orientation, we still have a minimum error of around 5 centimeters. This is due to the fact that there are many aerodynamic turbulences, unmodeled or uncertain modeling parameters in the model that we cannot precisely compensate for. So a solution for improving this precision, aiming at a precision that goes below 1 centimeter, we start adding an active manipulator that can therefore compensate for the oscillation of the robot. In the specific case, we design a delta arm that is known for its precision to basically drastically improve performances, going from a 5 centimeter error at the end effector to 2 centimeter error. But this for us was not enough. We wanted to do even better, and being inspired by the fact that contacts actually bring stability during operation, we then design what we call a smart end effector, which is composed of 3 omni wheels that guarantees a stable 3 contact points with the surface. And this end effector is then attached to the aerial platform with a compliant structure. And thanks to this smart end effector, let's say, we then reach a precision of below 2 millimeters. So then let's move to see how we can actually control those aerial manipulators, especially for complex tasks. In fact, one of our goals was to go beyond the interaction with static environments, but actually being able to manipulate dynamic and articulated objects. So now we don't only have to face the challenges coming from the complex dynamic of the robot alone, but also with the one regarding the environment. So now we have also to count for the dynamics of the environment. And we have to, while these two dynamic systems interact with each other, we always have to preserve stability, which is a non-trivial problem, of course. So the interaction with articulated object, we can only find few works addressing this problem. And those are either based on heuristics, so based on a pre-planned trajectory, or with the MPC method, model predictive control methods, that are anyway based on normally a rigid grasp or the assumption of having a very stable contact. So therefore, at the end, when we look at this proposed solution, we can see them as a sort of ad hoc solution, because they have been designed specifically for one specific task or one specific object to manipulate with. On the other hand, we foreseen a more general framework that can be used for different type of tasks and relies only on non-prehensile contacts, which those introduce some discontinuity in the dynamics because of their switching nature. And because of this, we cannot easily consider them in standard MPC approaches. So our way was instead to rely on what is called Model Predictive Path Integral Control, or MPPI controller, which is basically a sampling-based version of an MPC controller, which tries to find the feedback policy pi that minimize the expected infinite time horizon. So practically how it works is that we basically sample a sequence of input over the time horizon through a certain probability distribution, and then we forward simulate those inputs according to the dynamics of the system. we repeat those simulations for multiple in parallel simulation called rollouts to compute basically the cost of each of those rollouts. And then we take basically the input that lead to the minimum cost, and this we send to the robot, and we repeat the same process over and over at every optimization step. So one very good property of this is that we don't need anymore the differentiation of the dynamics. In fact, we just need to be able to forward simulate the sampled input. And thanks to this, we can just use a physics engine that is known to simplify somehow the simulation of contacts, which instead this could not be possible on a standard MPC. On the other hand, we have to simulate multiple times at real time the full system. And this increase the computational cost, and so decrease the frequency of the controller. In fact, for example, it is impossible with this technique to directly control each propeller of the robot. So we cannot directly control each actuator of the robot. So how to deal with this is we proposed a cascaded approach. So we relied on a first low-level controller, which is an impedance controller that in practice makes the system, the aerial manipulator stable and at the same time compliant with the environment, basically making the system looking like a second-order system. And instead now we used as a higher level controller this MPPI strategy that from one side can just use the simplified closed-loop dynamics of the full system, so this is a second-order system, and it is it can reach a good frequency, not to be a direct controller, but rather a trajectory generator for the low-level controller. So thanks to this approach, we managed to provide a framework that allows the robot to manipulate different type of object. Here you can see two examples where we open a door or open a valve with a minimum engineering effort, because we just have to change basically the simulation environment. And we don't have to change at all, instead, our framework. And because of the higher level controller replan online the trajectory, we also get this replanning feature that allows the robot to be from one side compliant to external disturbances, but also able to resume the task as soon as these disturbances goes away. Well, so far it looks very great. We can achieve a very amazing task, but those works only when the environment is very precisely known. And of course, because of noisy measurement or error in the estimation, this doesn't work when we are in the real field. In fact, here we have to consider, for example, friction coefficient, inertia parameters of the environment, or geometric parameters that are instead unknown. So in the literature, one of a very powerful tool to address these problems of uncertainty in the model is adaptive control. So the principle is basically to keep the same controller, but find a better suited parameters or gains of the controller that better adapt to the current situation. And this is done basically inferring it directly from the sensors. However, for example, taking as an example the problem of sliding the end effector along an unknown surface, finding this policy that directly find the optimal gains from the sensor is a very complicated problem. So what we instead thought to somehow rely on learning. We hypothesized that a learning-based network can instead somehow learn this adaptation policy directly from sensor to the gains of our controller. And in specific, we use reinforcement learning, use this methodology called teacher-student policy that works in this way. So first, we train in simulation a first network that is the teacher that learns basically how to adapt the gains of the controller when the full parameters of the environment are known. So the teacher knows everything of the environment and just needs to find the optimal gain for the controller. On the other hand, then we train a student, that is the network that will be then deployed on the robot, that is trained to imitate the teacher, but only having access to the real sensor, that in our case are the camera and a force torque sensor at the end effector. And we show that this approach can finally lead to much better performance when, for example, we try to slide an end effector along this very cumbersome rock-like surface of which the geometry and the friction coefficient are unknown. But there is still a very important point to be addressed in robotics, which is safety. So even though our robots can be able to do very amazing tasks, we need to provide some guarantees of safety. And in our case, safety means being able to provide guarantees of stability and also respecting some input or state constraints, like, for example, input limitation or obstacle avoidance feature. So regarding stability, a very powerful tool to prove the stability of a dynamic system is passivity. This is a mathematical tool that basically looks at the robot and the environment as two dynamic systems exchanging energy with each other. And looking at the autonomous system, so both the combination of both robot and the environment, we can say that a system is passive and so stable and safe if the total energy of the system does not increase. Well, with the type of object that we are interacting with, we can say, or we can actually assume that the environment is passive, so doesn't create energy in the system. But on the other hand, we cannot directly say this for our controller. So the controller and the specific, for example, the adaptive strategy that I just presented before, this is a non-passive action. So it can actually lead to the increase of the total energy of the system, and therefore to the destabilization of the overall system. So how to address this without changing the full framework that I presented before was to introduce this safety layer. So what we want is basically to find a new control input U hat that is the closest to the nominal input U provided by our controller, but that still ensure the stability and the safety of the system. And to do this, we combine two methodologies that are energy tanks and control barrier functions. So let's start with energy tank. This is another mathematical tool that introduces basically a virtual storing energy, storing element energy in the system. You can see that now basically the total energy of the system is the robot, the environment, and also the tank. And basically the energy that we accumulate, that we start with in the tank, and we can even accumulate, is used basically to compensate for the non-passive actions of the controller in order to make overall the full system passive. But of course, this can work only if there is energy in this tank. So therefore, now we have a new constraint that is that the system does not have to deplete all the energy that has been that is in the tank. So therefore, this new let's say stability constraint plus all the state and input constraints basically defines what we call a safety set. So a subset in the state space where we would like the system to always stay. So in the specific of this safety layer, we would like that this safety layer finds the a new input U hat that is the closest to the nominal one, but which keep the system in this safety set. So in general, this first problem is very complex to be solved, but instead using control barrier function, we have actually a way to transform this constraint optimization problem in a QP problem, which is much simpler and fast to be solved. And here you can see how this safety layer works in a practical example. Here we tested on a ground manipulator, but it could be also applied to our aerial manipulator. In the specific, we are actually applying the same MPPI strategy, but here on a grounded manipulator. So in this task, the robot will try to open this door, but inside the door, there is a little rope that while the door get open, it will get taut, and so will make the door not be possible to open it fully, and this the robot doesn't know. And you will see that without using the safety layer, so the robot tries to open the door, but when this rope gets taut, the robot, since it doesn't know, it will try to push and push more to make it open, basically at a certain point violating the passivity, reaching the point at which the robot is almost like letting the full furniture fall down, and at a certain point even breaks the cable, and the human needs to intervene to stop everything in order to bring back the system to safety. On the other hand, when we use this safety layer, you will see that as soon as the robot reaches this constraint of the door, the energy starts to be depleted, but as soon as it gets close to this limit, the safety layer basically limit the interaction force and preserve the stability of the system, making the full operation very safe. And once actually the operator cuts out this little rope, then the robot can resume the task in a very safe way. So this work basically showed a very complete system for single robot operation. But then I also tried to investigate how multiple robots can physically interact with each other. In the specific, I tried to design a multi-robot system that is physically connected with each other, able to perform complex physical interaction tasks. Here, not only we have to deal with all the challenges of single robot operation, but also with the additional one related to the complexity of the coordination and communication between the robot. For those, we design different type of control methods, in the particular case to manipulate cable suspended loads. And for this, we focus on centralized position and compliant control strategies that allowing to perform tasks like pick and place and assembly of some object. But we also try to investigate how to decentralize those strategies without the use of communication at all. So using instead forces as an indirect communication channel between the robots. And then let me briefly also introduce the work that we have done instead on the topic of human-robot aerial physical interaction. So this topic is very poorly addressed in aerial robotics, most likely due to the fact of the complexity of the problem, because now the robot not only have to interact with humans that are very complex dynamic system and very uncertain as well. Not only this, but we also have an extra requirement for safety and robustness. Therefore, due to this gap, I really try to investigate this topic, trying to address probably one of the first systems in which an aerial robot is tightly physically coupled to a human. In the specific, we have an aerial robot that is connected by a rope to the hand of a human. And we want the robot to be able to guide the human using only forces as a communication channel. And so you can immediately see that a possible application could be, for example, to guide visually impaired human along uncertain environment. So here the challenges, again, are the new physical interaction between the robot and the human, and also this extra need for safety and stability. So to address this problem, we design an admittance control framework that makes, from one side, the robot able to be compliant to the physical interaction with the human, but also allows to control the force that the robot is applying, thanks to the rope, to the end of the human. And on top of this, we design a force reference generator that basically decide which is the best force that the human should feel to guide them along a desired path. And since for us stability was giving proof of stability was one of the requirements, we also, thanks to this approach and a specific modeling of the system, we managed to provide the proof of stability and robustness using both Lyapunov theory and passivity theory. Here is how the system works. So basically, you can see that the robot is able to pull the human along this desired trajectory, here visualized in orange, that is not known by the human. Here, the human is not blinded for safety reason, but we ask him to only look at the ground and not at the robot. And you can see that at the end of the trajectory, the robot will place itself on top of the human, making him understand that the task basically it's over and he arrived at destination. Okay, so in this first part of the talk, I presented all the work that we have been doing, trying to improve manipulation capabilities of aerial robotics. But of course, our job is not done yet. There are still a lot of work to be done in order to bring aerial manipulators into real environments and so finally achieve the final goal. And therefore, in the next part of the talk, I will show you how I intend to continue my investigation toward this goal, still following these three major axes of research. So starting from the single robot operation, what we reached so far are the capability to perform also complex manipulation tasks, but with pretty low robustness and also in very controlled environment, always using the motion capture system. So the next step will be to relax this strong assumption, trying to design new methodologies to have a reliable complex manipulation in a real environment. And for this, I will address the problem in a twofold way. So from one side, from a low-level point of view, we want to conceive a new aerial manipulator that instead of having kinematically controlled motors at the arm, we want to replace them with torque control motors in order to be able to compute truly full body controllers that also allows to have multitask optimization. And then from a high level point of view, instead, we would like to include much more the perception into the framework that I just presented before. And perception, both in terms of visual and haptic feedback. So we would like to include cameras, but also we would like to include skin-like sensor at the end effector in order to provide not only the vision sense to the robot, but also the haptic sense to the robot. And this investigation will be carried out in the two projects that I got last year. One is called Higher Handy Bot, that is a national project, and the other one is called AeroTouch, that is instead an area project. Regarding then, we would like to somehow also move toward the multi-robot aerial physical interaction. Here, the work done so far basically show that, yes, we can do simple transportation task, again, using mostly centralized methodologies. So in the next step, I will try to bring this capability of interacting with the dynamic and articulated object also to the multi-robot scenario, trying to extend those strategies also in a decentralized sense and using onboard sensors. And for this, we will try to investigate the use of, for example, distributed optimal control applied both from the control point of view, but also from the estimation point of view. Last but not least, also regarding the human-robot interaction, the work done so far mainly cover a very simple task, which is this guidance of a human, where only the robot is an active agent, while the human in this specific case was only passive. And so in the next step, instead, we would like to focus on more collaborative tasks where the two agents, robot and human, are both active, for example, for collaborative transportation. Not only this, but we would like also to include much more human factors in our framework. Therefore, we would like to, for example, rely on the strategies that I presented before, so optimization-based method to include the human model, but also the capability to, for example, detect and react to human intentions. And along all these, of course, we will have to focus also in providing guarantees of stability, both from the control point of view, but also from the design point of view. So I really believe that this investigation will lead to the next generation of aerial manipulators, bringing the manipulation capabilities to the next level. And I'm very happy to be in the I think it's a very particular and enthusiastic moment to be working with the aerial robotics, because there are plenty of new ideas and projects going on, and I'm very happy to be part of this community that is really pushing hard the limits of both scientific and technological boundaries of aerial robotics, to have one day aerial manipulators in our daily life. So of course, all this would have not been possible, could not be possible without the brilliant minds of my team that I have here at INRIA, but also all the great people that I had, the great people, students, and so on, that I had the chance to work with along my journey. I also have to say I was extremely lucky to have great mentors. So thank you, Ruggero, Paolo, Roland, and Antonio, for giving me the tools to grow from a simple master student from the researcher that I am today. And also I take the occasion, of course, to thank all the jury members to take the time to be here today, and especially the reviewers that took the time to also read my manuscript and provide very insightful comments. Last but not least, I take this unique opportunity to also thank all the loved person, family, and friends that support me also outside the lab, and especially I want to thank my parents that unfortunately could not be here today. So with this, I conclude. Thank you all for your attention, and I'm ready for the question session. Thank you very much.